Welcome back to my channel. Today let us learn about optical activity in sulfur containing compounds. Sulfur is a non-metal. Elemental sulfur is yellow in color. It belongs to period 3 of the periodic table. It has an atomic number 16 with electronic configuration neon 3s2 3p4. The valency of sulfur varies from -2 to +6. That is, we can say that sulfur has extended valencies, which is similar to phosphorus. And the reason behind extended valency is when we look at the valence electrons of sulfur and the orbital, it is 3s2 and 3p4, and the next higher orbital is going to be 3d. So when we talk about the d orbital, we know that d orbitals can accommodate a maximum of 10 electrons. So the meaning is that when sulfur undergoes hybridization, the electrons, each electron of the orbital on 3s and 3p can jump to 3d, and this creates a varied amount of compounds that can be generated, both organosulfur as well as inorganic compounds containing sulfur. So hence sulfur has extended valency that is similar to phosphorus. So the reason I have mentioned here, this is because their valence shell has enough orbitals to accommodate more electrons. That is, for sulfur it has vacant d orbitals to accommodate the electrons. Organosulfur compounds are the organic compounds that contain sulfur. They occur in living body in the form of cysteine, cysteine, methionine. Also, sulfur is available and is found in vitamin B1. It is found in penicillin. It is also found in biotin, to name a few. The two main groups of organosulfur are sulfoxides and sulfones. Talking about sulfoxide, the oxidation state of sulfur in sulfoxide is 0 with valence electrons 10. So as we all know how to find out the oxidation state, if I have to write down the oxidation state of sulfur, which I have to find as X, and we know oxygen has a oxidation number of -2, and when I consider methyl and the ethyl group as +1 each, so it's going to be -2 + 2 is equal to 0. So hence the oxidation state of sulfur in sulfoxide is going to be 0. This lone pair we are excluding because lone pair we're not giving, doesn't have any oxidation number. Hence we are only considering the oxidation number on oxygen and also the methyl as well as the ethyl group. So the oxidation state of sulfur in sulfoxide is going to be 0. And when we talk about the valence electrons of sulfur in sulfoxide, it is going to be 10. Again, including the lone pair, it is going to have 10 valence electrons. Next organosulfur compounds is going to be sulfone. So in sulfones, sulfur has an oxidation state of +2 and sulfur has 12 valence electrons. So here you can see very clearly that you have 2 oxygen and 2 R groups. So if I consider each oxygen to have an oxidation number of -2, so -2 is going to be +4, and each R group has 1, so -4 + 2 is going to be, so we can consider it as -4 + 2 is equal to X, so X is equal to +2. Okay, so this is how we are finding out the oxidation state of sulfur in sulfones, which happens to be +2. Next, let us learn about the chiral sulfur. So here this is an example of a sulfone, and this is a chiral sulfone because we know that according to chirality, the central atom, whether it is carbon or phosphorus or nitrogen or any other atom, should have 4 different ligands around it. So when you look at this example, you can see the sulfur is the central atom, and when we look at all the 4 atoms around it, it is all different. So on the right side you have a toluene group, on the left side you have a toluene, on the right side you have a methyl, and then you have oxygen 16 and oxygen 18. So they are the isotopes of oxygen, and hence you are giving a star on sulfur, which says that it is a chiral sulfur. So, and this chirality is being created only because of isotope. Okay, or if it was not having any isotope on oxygen, then it would have been an achiral sulfone. But since it is an isotopic sulfur with oxygen 16 and oxygen 18, hence it is having, or it is, you can call it as chiral. Similarly, you can also see the chiral sulfoxide. So here also it's the same, like you can observe on the left side you have a carbon 12 isotope, on the right side you have a carbon 13 isotope on toluene, and then you have a double bond oxygen, and also you have a lone pair. So this again is creating a chirality in sulfur with all 4 different atoms around it, and hence it is a chiral sulfoxide. And whenever you have a chiral atom, we know we need to represent it with a star. Now also, along with the sulfoxide and the sulfone, the sulfur as an organosulfur can also be found in the sulfonium salt. So sulfonium salt is also another example of a sulfur containing compound, wherein the structure of this both sulfonium salt and sulfoxide is pyramidal in nature. So now coming to the enantiomers. So here it's an example of a methyl paratoluene sulfoxide, and you can see how they can easily be resolved into enantiomers. Sulfur containing chiral sulfur can easily be resolved, especially in sulfoxide can easily be resolved into its enantiomers. And you can see here on the left side we have the S enantiomer, and on the right side we have the R enantiomer. So these are the 2 enantiomers on sulfur. 2 enantiomers of this following sulfoxide. Next, coming to some of the biological importance of sulfur containing compounds, we have sulforaphane. Sulforaphane occurs in nature in broccoli, which is used as a vegetable in most of the times in salad, green salad. So this compound induces increased activity in certain enzymes which degrade carcinogenic compounds in the liver. So that's why most of the people have salads during their meals, because it always increases the antioxidants and decreases the radicals in the body. So this is the structure of the sulforaphane, and the nomenclature of it is named as 1-isothiocyanato 4-R methyl sulfonyl butane, which is called as sulforaphane. And here again you can see how it is a chiral sulfur. Okay, and then they have 4 different groups: methyl on one side, then you have isothiocyanate on one side, and double bond oxygen on one end, and lone pair on the other end. So hence this again becomes a chiral sulfur, which is also having biological importance, that is in broccoli. Okay, then we have some of the other sulfur containing compounds, coming to sulfonic ester and also sulfonium salts, which we already discussed. So sulfonic ester has a general formula RSO2R prime. So here again you can see how this 2 are the enantiomers of the particular sulfonic ester, and what we can observe here is the sulfur atom is chiral again here, with double bond with oxygen ethoxy group, and also the methyl benzene and also the lone pair on it. So there are 4 different ligands around the sulfur atom, which makes it chiral. Now coming to the assigning RNS configuration, you can see here very clearly that always the lone pair is given the least priority. So hence we number the lone pair as 4, and highest priority always given to oxygen because it's more electronegative. and double bond O gets the first priority, and ethoxide OET is getting the second priority, and the third is going to be for the substituted benzene, and the fourth is going to be to the lone pair. And you can observe here the direction is like anti-clockwise, hence it's going to be assigned an S configuration, whereas its enantiomer on the right side is going to be assigned R. Again, let's give the numbering for this sulfonic ester. We have oxygen with numbering 1, and we have ethoxide as numbering 2, and we have again the substituted benzene as 3, and we have the lone pair which we are giving the 4th position. Again, when we look at the number, it's against like the clockwise direction, and hence we are giving or assigning the configuration for the sulfonic ester as R. And you can see easily that S and R, or these two, are going to be the enantiomers of each other. Similarly, we also have a sulfoxide. So in sulfoxide, again, there is we are giving or assigning RNS configuration. So first is always given to oxygen. First we are giving to oxygen, and second priority goes to phenyl group, and the third priority is goes to the methyl, and fourth is for the lone pair. And you can see here it's again going the clockwise direction, and hence we are assigning it the R configuration. Next, some more examples of sulfoxide. We have carboxymethyl sulfoxide, para aminotolulyl sulfoxides. And the next group of the organosulfur compounds is going to be sulfines. So again, sulfines are considered to be rigid, and they are non-linear group. And the sulfines can easily be prepared by oxidation of thioketones with peroxy acids, which is going to give rise to the two isomeric forms in equal amounts. Next, let's assign RNS for some more examples. So we have a sulfone, we have a sulfite, and we have sulfonamine. Sorry. So first, starting with the sulfones, when we do the numbering here, again, all of these are the chiral sulfur. When you talk about oxygen, again, the highest atomic weight is going to be O18, so hence we are giving it first priority. Second is going to be for O16. And between benzyl and phenyl, we are going to give phenyl as the third priority and the benzyl group as the fourth priority. So here you can see that the least priority is also wedge, so it's going to be clockwise direction, and we're going to give it the R configuration. The least priority is going to be the benzyl. You can already see here it's been given here in the dotted lines. Let me just show it here. So you can see this part is given the dotted lines, which says that it is dashed and away from the viewer, and hence we are going to retain the configuration as R. Next, coming to sulfite. So when you look at sulfite, again it's a chiral sulfur group here, and we have oxygen on one end, so it is going to be given the highest priority. And among ethoxide and methoxide, we are going to give ethoxide as higher priority because it has higher atomic number. And third is going to be for methoxide, and fourth we will be giving it for the lone pair. So here again you can see the lone pair is already, it's in the dotted line, which says that it is the dashed away from the viewer. And just checking with the clockwise and anti-clockwise direction, it is going to be clockwise, and hence we are going to give it as the R configuration. Next we have for sulfonamine. So for sulfonamine, let us do the assigning of RNS configuration. So again here first starting with nitrogen, since we have nitrogen here, and nitrogen is having is more electronegative compared to oxygen and having a higher atomic weight than oxygen. So hence we are giving it, a higher atomic weight than carbon. Hence we give it the numbering 1. And second group is for phenyl. Third is going to be for methyl, and fourth is going to be for the lone pair. And here again you can see the lone pair is on dotted line, which says that it is dashed away from the viewer, and hence we are going to give it an R configuration, and with retaining the configuration. There's no reversal or anything because the least priority is already away from us, and hence we are going to assign it the R configuration. So this was all about the chirality or optical activity of sulfur containing compounds. Thank you very much.